Hi, I'm Jason Perro, a graduate student in the physics department at UTA. I will present some of the research I've been doing with Dr. Weinberg on hydrodynamic models of radiation-driven winds from type 1 X-ray bursts. X-ray bursts occur in binary systems where mass is transferred from a companion star to the surface of a neutron star. A neutron star is an extremely dense, crushed stellar remnant, basically a ball of neutrons supported by degeneracy pressure, with a total mass of approximately 1.4 solar masses packed into a 10-kilometer or 6-mile radius. As hydrogen and/or helium accretes onto the surface of the neutron star, the material heats up and ignites. Thermonuclear burning of the accreted material generates a photospheric radius expansion, or PRE burst, which is detectable in the soft X-ray band. It is important to study X-ray bursts to facilitate better interpretation of high-precision observational X-ray spectra. This in turn will improve radii and mass measurements for neutron stars to determine the high-density equation of state. This is motivated by enhanced capabilities of the Neutron Star Interior Composition Explorer, or NICER, an instrument installed on the International Space Station, which investigates the structure and dynamics of neutron stars via X-ray spectroscopy. NICER offers improved spectral resolution and sensitivity over its predecessor, the Rossi X-ray Timing Explorer, with a bandpass reaching down to 0.2 kiloelectron volts, which makes this instrument ideal for studying the soft X-ray portion of PRE bursts. Identification of metals in PRE burst spectra could be signatures of ashes ejected during nuclear burning. We use the open source software package Modules for Experiments in Stellar Astrophysics, or MESA, to build a suite of hydrodynamic models of photospheric radius expansion X-ray bursts. We start by simulating the hydrostatic evolution of the atmosphere, including convective mixing of ashes and radiative diffusion. Next is the hydrodynamic evolution of the photospheric radius expansion wind. We follow the launch and progression of the wind, including identifying heavy element ashes in the wind and the cooling phase when the photosphere falls back to the neutron star's surface. Figure 1 shows the top of the convection zone for different times during the burst rise leading up to the start of the wind. The convection zone moves outward and mixes the burned ashes at lower column depths as indicated in Figure 2. The material above the convective region is then purely radiative and can diffuse outward without being overrun by the convective region. The radiative region heats up and eventually reaches the local Eddington limit. When the Eddington limit is reached, the convection zone recedes and the atmosphere becomes fully radiative, and any excessive luminosity above the Eddington limit powers the launch of a radiative wind from the surface. This transitions the model into the hydrodynamic wind phase, where figures 3 and 4 show for the first second of the wind how the luminosity becomes super Eddington at deeper column depths and higher densities. The heavy element ashes in the deeper layers are then ejected with the wind. In conclusion, it is clear that evolution and composition of the wind is sensitive to the accretion rate and composition parameters. In general, slower accretion rates and more helium-rich accretion material result in more energetic winds, with larger PRE bursts and heavier element ejecta, which could leave an imprint on the spectra of observed PRE bursts. With the completion of the hydrostatic phase analysis, we will continue with additional analysis of the hydrodynamic wind phase for both the pure and mixed hydrogen-helium accretion models. Thank you very much for listening to my presentation and enjoy the UTA Discover Research Symposium 2023.